push that rock here with some cement. Let's grab a trig function. So we want to graph y equals sine of x. So I have a Cartesian plane here. We're going to follow the tradition of letting the horizontal axis be the input axis, and we're going to follow the tradition of letting x represent the inputs. We're going to follow the tradition on letting the vertical axis be the y-axis, and we're going to follow the tradition of y representing the outputs. Okay, so we have inputs along here, outputs along here. Now this can be very confusing because we're graphing outputs are y, the sine function, the inputs are x. But our definition, when we define a trig function off the unit circle, we have a unit circle described by the equation x squared plus y squared equals 1, meaning the radius is 1 unit. This distance here is 1 unit, that distance is 1 unit. The distance from here to there is also 1 unit, okay? The inputs though are some angle. So if I have some angle, like say a 90-degree standard position angle, that's the input. But we'll use radians. So pi halves radians is equivalent to 90 degrees. So the input is a angle measurement, how fat the angle is, and the output is a y, okay? So, but over here, the input is x. So you just have to remember that x is representing the angle measurement, okay? So back to our definition, sine of theta in the unit circle is the y-coordinate where the angle theta intersects the circle. So when the input is pi halves radians, the output is 1. So when the input is pi halves radians, the output should be 1. Okay, what about if the input was 0? 0 would mean that I don't rotate any at all. Well, the output there is 0. So when the input is 0, the output is 0. So when the input is 0, the output is 0. What about if I rotate 180 degrees, or which is equivalent to pi radians? So if I go, let's do it in a different color, I guess. I have a standard position that rotates 180 degrees, or pi radians. So my input is pi radians. Then my output would be 0 again. So when I'm graphing over here, my output is 0 when the input is pi radians. What about at 3 pi halves radians? Well, that would be a rotation all the way to here. That's 3 pi halves radians. And the output is negative half. So when the input is 3 pi halves, the output is negative 1. And then finally, if I rotate 2 pi radians, I'm back to 0. And so the graph goes back to 0. And if I keep rotating, so that I've rotated 2 pi and I go another half, so 5 pi halves, I'd be back to 1, and the graph is going to repeat itself. And they call these periodic functions because over a period of the inputs, it starts to repeat itself. And so the graph looks like this. Now, with just this, you might think, don't graph this. You might think that it does this. You know, but that's terrible. That's not actually the case. We skipped over a lot of inputs. The graph actually looks more like this. It has a curve to it. How do I know that? Well, you know, try some of the inputs we skipped over, like pi fourths. We skipped over that input. So if we go to pi fourths, which is this angle right there, we know that the coordinate point where a pi fourths angle intersects the circle is root 2 over 2 comma root 2 over 2, and the output for sine is root 2 over 2. Root 2 is close to 1.4. You cut 1.4 in half, you have about 0.7. So the output, when you put in pi fourths radians, the output should be really close to 0.7. And notice When the input is 0.4, here's 0.5, 0.6, 0.7. So there it is at 0.7 like it should be. So that's how you know it's not just going linearly up, but has this curve to it. That's how you graph a sine wave. Math made simple, Simpson math.